flat top sampled PAM. The other day I told, because in natural sampling, during the pulse interval tau, the amplitude of the pulse is not constant, but it is varying. As a result, during that interval of time, the amount of transmitted power is not constant, it varies. Now, what we do in flat top sampling is we see that the top of the pulse is flat. So for that, again, I use a natural, instantaneous sampling or ideal sampling circuit where I have a multiplier. I have a multiplier here. So one input to the multiplier is M of t, and another input to the multiplier is C of t. C of t is the pulse train, impulse train, from which I can get, let it be S1 of t. So ideal sampled signal, the same multiplier we have seen in the previous class. See, I have used a multiplier M of t and C of t. So generated S of t. S of t equal to M of t into C of t, where C of t can be expressed as sigma 1 to infinity delta of n minus Ts, where Ts is the sample time interval. So this is my instantaneous sampled signal. So we generate the same signal. So this signal we are considering it as S1 of t. Okay, here. S1 of t. So S1 of t is the ideal sampled signal. Now what we do is the width of the impulse. The width of the impulse is very, very small. We can call it as infinitesimally small of duration delta t. So if I could able to increase that width of the pulse, I could have a circuit which can increase the width of the pulse. Then my output S2 of t is a flat top sampled pulse amplitude modulated signal. So such a circuit where I want to increase the width of the pulse, such circuit can be called as, say, pulse broadening circuit or network. So this is the basic block diagram, I can say, to generate the flat top sample signal. Now here, the first part, you know how to generate S1 of t because we have already dealt with the ideal sampled PAM. The job of the pulse broadening network is to increase the width of the pulse. So let's C of t equal to sigma and running from 1 to infinity delta of n minus t minus nts. Okay. If I apply Fourier transform to this, my C of f will be Fourier transform of sigma and running from 1 to infinity delta of t minus nts. Now, can anyone tell me, because your this thing is already over, your signals is over, what is the Fourier transform of a simple rectangular pulse? Let it be rect of t. What is the Fourier transform?
1.
1. Okay, if that is 1, what is the Fourier transform of delta of t?
1.
Both are 1. Fourier transform of impulse. Not only Fourier transform, you take any transformation of impulse, it is 1. But my question is, what is the Fourier transform of a rectangular pulse?
Ramp signal.
Ramp.
Sinc function.
Sinc function. So you are on the lottery. What is it? 1, ramp, sinc. Any other answer? My time duration is tau. Then this is a sinc function. Fourier transform of a rectangular pulse is a sinc function. Omega tau by 2 divided by omega tau by 2. Or simply tau sinc of omega tau by 2. Okay. So with this basics, because I said this is a network. Okay, this is a pulse broadening network which increases the width of the pulse by output S2 of t. Pulse width is more compared to S1 of t pulse width. So when the width of the pulse, if you take one pulse and the width of the pulse is broadened, then my impulse will then become a rectangular pulse. Okay, fine. So my idea is to realize what actually this pulse broadening network is, or at least if we could able to find the transfer function of pulse broadening network, then we can proceed with the rest of the details. So what is the transfer function? Transfer function of pulse broadening network. So that is my very next question. So because we know that transfer function is always represented by h of j omega. Okay. So transfer function of this signal, sorry, this pulse broadening network can be defined as the Fourier transform of the output signal divided by Fourier transform of the input signal. Sorry. Right? And as I said, my output is a rectangular pulse. My output is a rectangular pulse. So therefore, for a rectangular pulse, Fourier transform would be, just now I told, tau sine tau omega tau by 2 divided by omega tau by 2. Fine. What is the denominator? My denominator, I said, here I have an impulse Here I have an impulse, okay, whose width is given by dt. Assume the magnitude is 1. So the area under this impulse will become, the height of the pulse is 1 and the width of the pulse is dt. So therefore the area under the curve will become dt into 1. Or after simplification, my Fourier transform of pulse broadening network would be tau by dt into sine omega tau by 2 divided by omega tau by 2. So here we can decide with tau, and omega, and we can realize the pulse broadening network. Now we arrived the transfer function of pulse broadening network. Anyway, the before part we know. This is an instantaneous sample signal, a PAM. So that's all about the small mathematics part as far as flat top sample signal is concerned. Now to generate this, how the generated S2 of 2 will look like, or how S2 of t is generated from S1 of t. We know how to generate S1 of t from M of t and C of t. These two are multiplied. C of t is the impulse train, M of t is the message signal. So let us have a look at the waveform. Assume I have M of t something like this. Sorry. Let the M of t will be. This is my M of t. Let it be. Or let me extend something like this. And I have a train of impulses at every sample time Ts. So each impulse is having a width of dt. Of course, dt is very, very small. So this is my C of t. So from which I can generate S1 of t as, this is my, at every sample time duration, I can have my signal. Now, so this S1 of t is given as input to the pulse broadening network. And the job of the pulse broadening network is, let it be, again, let me draw that S1 of t. For instance, I am drawing. You can synchronize in time. So when this is given to the pulse broadening network, the job of the pulse broadening network is it will increase the width of the pulse like this. It simply increases from dt to tau. If you observe carefully, the height of the pulse is constant. The height of the pulse is constant. So this is my S2 of t. Is that clear? No answer.
S2 of t height same as sir.
Come again. Come again. What is your question?
S1 of t, S2 of t height is same as sir.
S1 of t, S2 of t height is same. But the thing is, in a natural sampled PAM, the height of S2 of t will be something like this. It follows M of t. It follows M of t. But here, the same height, with the same height, the impulse is now converted into a pulse, rectangular pulse. With the same height, we are increasing the width. That's all. We are not changing the amplitude of the pulse. We are only increasing the width of the pulse like this with the help of the pulse broadening network. So therefore, this is my carrier and this is the ideal sampled signal, ideal sampled PAM, and this is the flat top sampled. For your understanding, I'll take one more example, one more waveform so that you can understand very clearly. I'll draw on the same how the flat top sampled signal will look like. Assume I have a signal like this. Oh, I have taken the same, let it be. Assume I have a signal something like this. So these are the intervals at which I'm taking the samples. These are the sample intervals, let us suppose. So now, in ideal sampling, I am taking this value. When I'm passing it through the pulse broadening network, when I pass it through the pulse broadening network, then my ideal sampled signal pulse width is now increased like this. Then I take the next ideal sampled signal, pass it through a pulse broadening network. Now I got like this. Again, you take another sample, you will get the flat top sampled signal, flat top sampled PAM signal like this. Again, you take one more. Of course, in flat top sample, you can observe certain amount of error. There is some deviation from original M of t and sampled M of t. So this is the deviation that you can observe, or this is the deviation that you can observe. I'll change the color so that you can understand more clearly. So this is the deviation that you can observe. So that is what we call it as sampling error. So here also there is a deviation, here also. Okay. So this is the flat top sample signal. Flat top sampled pulse amplitude modulated signal. Am I clear to you?
Yes, sir, clear, sir.
Okay. So now, having seen the flat top sample signal, let us move to the very next topic called how to demodulate. Demodulation of PAM. Now, whether it is an instantaneous sampled signal or a natural sampled PAM signal or a flat top sampled PAM signal, generation part is over. In an instantaneous sampled PAM, we simply pass both signals. One signal is M of t, another signal is impulse train, pass it through a multiplier. Multiplier output is your ideal sampled PAM or instantaneous sampled PAM, just like this one. Yeah, this one. Now in natural sampling, what we did is instead of taking impulse train, we have taken a pulse train. Okay. So this is the circuit for generation of natural sampled signal. We have taken a pulse train, and this switch can be operated, or you can use a transistor circuit where the base is given with C of t. So the base emitter junction will be forward biased when C of t is high. Therefore, the transistor is on. Therefore, the M of t, whatever at the input, appears at the output between emitter and ground across RE. When C of t is 0, there is no biasing between base and emitter. There is no biasing between base and emitter. Therefore, you cannot find any output at the emitter to ground. So M of t at the output is 0. So such that here, if you observe carefully, the top follows M of t, top of the pulse. Then we slowly move to what we call it as flat top sampled signal, where the output of ideal sampled PAM is given to a pulse broadening network. Can we imagine a pulse broadening network? Yes, we can imagine a pulse broadening network where the output pulse is a rectangular shape, where the input pulse is almost similar to an impulse, or having a very, very less amount of width called dt. So therefore, we got the transfer function of pulse broadening network defined as Fourier transform of output signal by Fourier transform of input signal. Fourier transform of output signal, it is a rectangular pulse, as someone said. So Fourier transform of any rectangular pulse is the sinc function, tau omega tau by 2 by omega tau by 2 divided by Fourier transform of S1 of t. S1 of t is an impulse. If you calculate the Fourier transform of impulse, it would be 1. But here I have a finite amount of pulse width called dt. Therefore, the Fourier transform will be the area under the curve. Height of the impulse is 1 and width is dt. Therefore, dt into 1 is the Fourier transform of S1 of t. So tau by dt into sine omega tau by 2 divided by omega tau by 2 is the transfer function of this pulse broadening network, and therefore we can realize we got the h of j omega for this. Now how to demodulate? How to demodulate a PAM signal? The circuit for demodulation, we call it as the circuit for demodulation of PAM. We use sample and hold. We simply call it as S by H, sample and hold circuit. Okay. You are following, right?
Yes, sir.
Yeah.
Yes,
So
sir.
how a sample and hold circuit will look like. Here I have the input signal, let it be V input of T, whatever. And I have a switch here. Let the switch is say S1, switch S1. And now I have a capacitor here. Okay. And I have another switch called S2. Let it be another switch S2. So now my output is V0 of T. That's all. This is a simple sample and hold circuit. We'll see one by one what is S1, what is S2, what actually this capacitor will do. Okay. Assume I have a input signal. Let it be assume I have an input signal something like this, where my sampled PAM, let it be the natural sampled PAM. My samples are like this. So therefore here I got the signal. Here I got the pulse. One more. Something like this. A natural sampled PAM signal, let us suppose. Okay. So now what happens is at every sample interval, let my sample interval, this is 0, T, 2T, or TS, 2TS, 3TS, so on and so forth, 4, 5, 6 TS. For example, I have taken 6. At every sample interval, my switch S1 is closed. So your switch S1 is closed at every sample interval. At every sample interval. Fine. When switch S1 is closed, whatever the input signal I have, my input signal, whatever the input signal I have, to that value, my capacitor is going to be charged. Because my S2 is already open. S1 is closed during the sample interval. So the signal cannot find a discharging path or a traveling path because S2 is open. So it will start, my capacitor will start charging. And I choose my capacitor in such a way that my time constant RC is very, very less, such that I can say my charging time of the capacitor is very small. Similarly, the charging time also, because time when you choose time constant is less, charging and discharging takes place almost instantly. So therefore, when charging of the capacitor is done and is fully charged to the this value, whatever the sample interval value. So therefore, that value will remain as it is at the output. So therefore, if you observe here, this value I mean this value, will remain until the next interval. Follow me carefully. Until the next interval time, this output will be hold across the capacitor. So across the capacitor, the same value or the sampled voltage will be held. Now, at the beginning of the next interval or at the beginning of the next sample time, what happens is my switch S2 is closed. My switch S2 is closed such that my output of the capacitor will be discharged to 0. Point number 1. And then once the capacitor is fully discharged, my S2 becomes open and S1 becomes closed. Try to understand my point. S2 is open after complete discharge of capacitor. Now my S1 is closed. When S1 is closed, during the same interval of time, my next TS value is this one. So this value is comparatively less than this value or almost equal, I can say. So let it be a small deviation. So until the next interval of time, the same value will remain. Again, my capacitor is brought to 0 just before the next sample interval. Again, my next value to which my capacitor is charged and held to the next value, again discharged, again charged. So if I join this or pass it through a filter, a low pass filter, this is my demodulated PAM signal or demodulated M of T, I can say. So these peaks, this is my demodulated signal. When I pass it through a filter, low pass filter, I'll get the same whatever I have used here, the same signal I can get here. So this is how we demodulate a pulse amplitude modulated signal. Forget about my input is whether it is an ideal sampled PAM signal or a natural sampled PAM signal or even flat top sample. The same circuit will give the output where my output is my M of T. Of course, you pass it through some filter here so that you can get a smooth curve of M of T. Whatever is used at the transmitter, the same M of T can be regenerated at the receiver. Something like this. Clear? I have to again check whether I am in the meeting or not, because there is no response from your side.
Clear, sir.
Okay. So let me explain the next topic. I'll give an introduction to the next topic called time division multiplexing. What is multiplexing?
Passing one or more signals.
Number of inputs, single.
Transmitting one or more signals through a single channel.
Perfect. In communication, the most scarce things are two things. One is channel. Channel is very limited. And the next one is bandwidth. Keep remember. Everybody want bandwidth. Everybody want channel. Channel, it may be a coaxial cable or free space air. If it is wireless communication, air is the only channel we have. So now if I want to transmit more than one signal into the air, in AM and FM, because we have a bandwidth from 540 kHz to 1650 kHz, or in FM 88 MHz to 108 MHz, 90.4 MHz will take a bandwidth of 200 kHz. 90.4 MHz will take 200 kHz. 93.5 will take 93.5 MHz channel will take another 200 kHz, so on and so forth. At a time they can transmit it. Now, out of 88 to 108, what is the total bandwidth we have? $88 to 108. Total bandwidth of FM. What is this entire band range? How much? 88 minus 108.
20 megahertz.
So 20 megahertz is allocated for FM radio broadcasting by Government of India. And I am saying that each channel will take 20 kilohertz bandwidth. If that is the case, you tell me between 88 to 108, how many number of channels can be transmitted at a time? Each channel 20 kilohertz. Total available spectrum is 20 megahertz. I want the number of channels. How much? You can use pen and paper, of course, your mind also. One radio station requires 200 kilohertz. I said a total bandwidth of 20 megahertz, that is from 88 to 108. How many number of radio stations can be set up within the band of 88 to 108? If each requires 200, then 20 megahertz, 20 mega divided by 200 kilo is 100 radio stations can be accommodated between 88 megahertz to 108 megahertz. That means from, say, this is 88 megahertz and this is 108 megahertz. So this is my first channel, second, third, fourth, fifth, so on up to 100th channel. Now, what is the x-axis here? X-axis.
Channels.
So channels are the numbers I made. I am asking what is this 88, 108? what is this?
Frequency.
Frequency. So because 88 to 108 is allocated for FM radio, commercial FM radio broadcasting, and we know that each radio station occupies 200 kilohertz, and we divided the available spectrum from 88 to 108. So the frequency is divided, and this type of thing is called frequency division multiplexing, because somewhere here I got 90.4 megahertz, somewhere here I got 93.5 megahertz. Now in your radio receiver on your mobile, you tune to 90.4, you can listen to 90.4 megahertz. Immediately after 10 seconds, you tune to 93.5 megahertz, you can listen 93.5 megahertz. That means your radio receiver receives all the signals all the time. This point is very important. But the frequency is limited for each channel. Such type of multiplexing, all these radio channels are transmitted into the air, but each channel is identified, or each channel is subdivided with their respective frequencies. Such type of multiplexing into the channel, all signals are transmitted at a time. So such type of multiplexing is what we call it as frequency division multiplexing. Can anyone tell me what is the disadvantage of frequency division multiplexing?
Sir.
What is the disadvantage of frequency division multiplexing?
Bandwidth is more, sir.
Bandwidth is not more, bandwidth is less. I'll tell. See, the advantage here is all the time we can transmit all the signals. That is the biggest advantage of frequency division multiplexing. But the problem is, I said, okay, one channel occupies 200 kilohertz. Assume instead of FM, if I go for cellular mobile, my required channel bandwidth is more. Instead of 200 kilohertz, assume 2000 kilohertz each channel requires. Then these 100 channels will now drop down to 10 channels. That means bandwidth is limited, but we can transmit all the time. If channel bandwidth increases, number of channels decreases. Try to understand. If channel bandwidth increases, number of channels decreases. That is the disadvantage of frequency division multiplexing. Now, what is time division multiplexing? Time division multiplexing is very simple. I have user 1 here, user 2 here, user 3 here. And now I want to transmit the signal from user 1 to the channel, user 2 to the channel, user 3 to the channel. What I do is I spend, say, 10 seconds at user 1, and I remove from user 1, the switch is moved to user 2. Here I spend 10 seconds. So user 2 information will be transmitted on the same channel. I spend another 10 seconds here. User 3 will be transmitted on the same channel. Again, the switch rotated to user 1. Now the advantage here is during this 10 seconds, whatever the bandwidth you want to transmit, you transmit to the channel. It is 200 kilohertz or 2 megahertz or 20 megahertz, whatever. Here bandwidth is not limited. So full bandwidth, infinite bandwidth you can transmit on the channel. After your turn, the switch moves to the second user. he also can transmit all the frequency, infinite bandwidth frequency. Then the switch is moved to user 3. He can transmit all the frequency. The advantage here is you can transmit infinite bandwidth. Can anyone tell me what is the disadvantage here? 10 seconds, 10 seconds, 10 seconds, I said. So time is divided across all the users. Again, it is rotated. What is the disadvantage here? Disadvantage of TDM. Assume my number of users instead of 3 if I have 1000. 1000 users are there. Then from user 1, user 2, user 3 up to user 1000, the switch moves. As a result, the user 1 has to wait, or delay comes into picture. Even though you can transmit all the frequency, time is limited. Time is limited. That is the disadvantage of TDM. Clear? FDM and TDM. I just introduced. I have not actually went into TDM. We'll discuss more on TDM.